Hello dear students, now I am going to discuss Cambridge A2 Chemistry May-June 2023 paper 42. A2 Chemistry, this paper 4, May-June 2023 paper 42. Please subscribe, like and share my channel. Let's move. First, number 1a, group 2 carbonate decompose when heated to form metal oxide and carbon dioxide. Number 1, suggest a mechanism for the decomposition of carbonate ion by adding two curly arrows in figure 1.1. So this carbonate ion goes to carbon dioxide and oxide ion, metal oxide. So you know carbon dioxide, carbon oxygen double bond, carbon oxygen double bond, and oxide ion you know given O -2. Here this bond 2 electron go to this oxygen, so this minus and one lone pair electron to become O2 minus. Then this carbon become positive, so this lone pair electron goes to here, it's form double bond. So this why carbon carbon double bond produce. Carbon carbon double bond is produced. Next, describe the variation in the thermal stability of group 2 carbonate. Explain your answer. Group 2 carbonate, you know, variation increases down the group. I mean thermal stability increases down the group. Down the group thermal stability increases. Now explain. You know down the group cation size increases, cation become larger as shell number increases. So charge density decreases as cation become larger, so charge density decreases. That's why cation polarizing power of cation decreases, so cation polarizes anion less. Cation, as cation charge density decreases, so cation polarizes anion less. That's why thermal stability increases. If polarization more, thermal stability less. If polarization less, thermal stability more. So thermal stability down the group increases. Why? Down the group cation size increases, charge density decreases, so polarization decreases, means cation polarizes the anion less. Cation polarizes anion less. Now definition B1, define lattice energy. You know energy released when 1 mole of a ionic compound is produced from gaseous ion. What is lattice energy? The enthalpy change when 1 mole of ionic compound is produced from its gaseous ions. This is the definition. Now number 2, you see lattice energy of group 2 carbonate become less exothermic down the group, decreases. The lattice energy of group 2 oxide also become less exothermic down the group. Lattice energy of metal carbonate and lattice energy of group 2 oxide, metal oxide, change by different amounts going down the group. Now suggest how the standard enthalpy change of decomposition of reaction for group 2 carbonate changes down the group. Explain your reasoning in terms of relative size of the anions. You have to mention size of the anion and relative changes in the lattice enthalpy down the group. You have to mention two things. One is lattice enthalpy, other is size of the anion. So how the standard enthalpy change of decomposition? Enthalpy change of decomposition become more positive. More positive means less negative. So become less negative down the group. Why? Because oxide ion is smaller than carbonate ion. Oxide ion, oxide ion is smaller than carbonate ion. Oxide ion O-2 is smaller than carbonate ion. So lattice energy of oxide become less exothermic faster. So lattice energy of oxide become less exothermic faster because oxide ion is smaller. So lattice energy of group 2 oxide become less exothermic faster. This is the difference. Now number C, potassium sulfide is used as a food additive. The concentration of sulfide ion can be determined by titration using aqueous acidified manganate 7. First, a 25 centimeter cube solution contains 3.4 gram of impure potassium sulfide. Mass is given. 25 centimeter cube of this solution requires 22.40 centimeter cube 0.0250 mole per dm cube acidified manganate to reach the end point. This is the titration. Manganate concentration and volume is given, so you can calculate mole. Then all the sulfide ions are oxidized. None of the other species in the impure potassium sulfide are oxidized. Only sulfide ion are oxidized. Now the reaction occurs as shown by the two half equation. This reaction are given. This one half equation, two half equation. Now first give the ionic equation for the reaction between sulfide ion and acidified manganate ion. So if you add this equation to half equation, you will get overall this equation. But when you add, electron must be cancelled, and to do electron cancel, every half equation must be equal electron. So here first equation is 2 electron, here 5 electron. That's why if you multiply by first equation 5 and second equation by 2, electron number will be equal. Then electron will be cancelled if you add. Now give the ionic equation for the reaction between sulfide ion and acidified manganate ion. So here 2 times manganate ion, 2 manganate ion, 8 to the 16 hydrogen ion, right hand side 10 hydrogen ion. So left hand side 16 minus 10 hydrogen ion. So left side will be 6 hydrogen ion. Then 5 times sulfide ion, 5 mole sulfide ion. Now right hand side, as 2 is multiplied, 2 manganese 2 ion, 2 manganese 2 ion. Water, now this is 4 to the 8 water. Now 5 ones are 5. So 8 minus 5, right hand side 3 mole water. Then sulfide ion 1 times 5 sulfate ion. This is the ionic equation for the reaction between sulfate ion and acidified manganate ion. Now calculate the percentage purity of sample of potassium sulfite. You have to show your working, and you see first moles of manganate ion. You see concentration is given, volume is given. So volume centimeter cube divided by 1000, you will convert into dm cube. First of all, moles of manganate ion concentration into volume, you get this mole of manganate ion. This mole you get. Then moles of sulfite ion ratio, moles of sulfite ion in 25 centimeter cube, 5 by 2. This ratio 5 by 2. 5 over 2 times manganate. So you get 1.4 times 10 to the power minus 3. This is in 25 centimeter cube, but this solution is 250 centimeter cube. You see in question, (250 centimeter cube) solution, but you calculate for 25 centimeter cube. 250 is the 10 times of 25. Now you see, so moles of sulfite ion in 25 centimeter cube, this moles of sulfite ion in 250 centimeter cube, 10 times more. So 1.4 10 to the power minus 2 mole. Then mass of potassium sulfite, number of mole into molar mass of potassium sulfite, so 2.2162 gram. This is actual mass. Now percentage purity, experimental mass or actual mass divided by calculated mass, 3.40 is given. Here 3.40 gram is given. So now percentage purity, experimental mass divided by calculated mass into 100, 65.2 or 65.3% you will get answer if you calculate. Now the potassium disulfide is another food additive. The disulfide ion has the displayed formula in the following figure. This is the displayed formula. Deduce the geometry means shape around the sulfur, here alpha sulfur. So you see how many bond present, 1 2 3 4. Around sulfur atom there are 4 bond. 4 bond means geometry or shape will be tetrahedral, and you know double bond in shape, double bond behave as a single electron pair. So total 1 2 3 4 pair of electrons surrounding the sulfur atom. So this shape will be tetrahedral. Next, number 2, state 2 typical chemical properties of transition element. You know, they form colored compounds, they form complex ion, or you can write they behave as catalyst, they show variable oxidation state. Now B, aqueous solution of cobalt 2 salt contains complex ion hexa means 6 hexa aqua cobalt 2. Define the complex ion. Complex ion, metal ion is surrounded by ligands. This is known as complex ion. This is a complex ion. Metal ion, cobalt ion is surrounded by water ligands. So define a complex ion. Metal ion is surrounded by ligands. Now is 2 samples of cobalt complexes are reacted separately with an excess of aqueous ammonia, with an excess of concentrated hydrochloric acid, with an excess of aqueous sodium hydroxide. In this diagram, cobalt complexes, excess sodium hydroxide C, excess aqueous ammonia A, excess concentrated sulfuric acid, hydrochloric acid B is produced. Complete the table. You will complete the table. You see, first reagent added to cobalt complexes, formula of the cobalt species form, then color and state the cobalt species form, type of reaction. Now you see, first an excess of ammonia, water ligand is 6 water ligand will be substituted by 6 ammonia ligand. So A product will be hexaamine cobalt 2. 6 water ligand will replace by 6 ammonia ligand. So this name will be hexaamine cobalt 2. Now color will be brown solution, or you can write cobalt is a brown, yellow brown solution. This is ligand substitution reaction or ligand exchange reaction. Now you see B, cobalt 2 complexes, aqua complexes reacts with when concentrated hydrochloric acid, and this octahedral geometry, but when it reacts with concentrated hydrochloric acid, tetrahedral geometry will be formed. So the product will be tetrachlorocobalt 2, and this is blue solution. This common reaction when if hexaqua cobalt 2 ion, if you add concentrated hydrochloric acid, tetrachlorocobalt 2 ion is formed, and this is color is blue solution, and this also ligand substitution reaction or ligand exchange reaction. Now you see, if aqua cobalt complexes, if you add excess sodium hydroxide, first will form cobalt 2 hydroxide, or you can write cobalt 2 hydroxide tetra aqua. If you write COS whole 2, you get marks, but actual this is the formula, tetra aqua dihydroxy cobalt 2, cobalt 2 hydroxide. This is precipitate, this is blue precipitate, or you can write pink precipitate. This is reaction type of the reaction will be is precipitation. As precipitate is formed, so reaction type is precipitation reaction. Now see, ethane dioate ion C2O4 negative 2 can act as a bidentate ligand. Number 1, explain what is meant by a bidentate ligand. Bi means 2. A species that donates two lone pairs of electrons to form two dative bond to a metal ion. I mean, bidentate ligand is 1, which donates 2 pair of electrons to the metal ion to form 2 dative covalent bond. Then here complete the 3-dimensional diagram of this. Show 4 stereoisomers of 2 ligand water, 1 ligand oxalate ion, 1 bromide, 1 chlorine. This is oxalate ion. C2O4 negative 2 ligand is representing by this. So total 2, 2, 4, 1, 1, 6. Total coordination number 6. So you can complete this diagram. Here is given already. So 2 water ligand opposite, 1 chlorine, 1 bromine. And now 2 water same side cis, this trans, 1 chlorine, 1 bromine. Then you can draw 1 water here, another water here, chlorine this isomer, and here also 1 water this place, another water, chlorine here, this chlorine here, bromine go there. So by arranging different ligand you can shows this 4 diagram. Now then you are asking state the oxidation state of cobalt in these complexes and type of stereoisomerism shown. So oxidation state of cobalt +3, why +3? You see oxalate -1, this -1, chloride -1, -1, total -4, to oxalate, -4, okay, -4 and -1 here left, so total -3. That means cobalt is +3, metal is total ligand -3, so cobalt will be +3. Here cobalt +3, and type of stereoisomerism will be cis trans, you can write, or geometrical, or you can write optical. You get marks. Let's move. Okay, now number 3, complete table 3.1 by placing 1 tick mark in each row to indicate the sign of every type of energy change under standard conditions. Energy change always positive, always negative, can be either negative or positive. Now you see bond energy always positive, so here tick mark. Enthalpy change of atomization always positive, energy is needed, so this positive. And enthalpy of formation always, it can be mostly negative but sometimes it can be positive, so enthalpy of formation can be either negative or positive here. Then define standard enthalpy change of atomization. You know, it is the enthalpy change when 1 mole of gaseous atom is produced from its elements under standard condition. And enthalpy change when 1 mole of gaseous atom is produced from its elements under standard conditions. Say 1 mole of sodium standard state solid It's from 1 mole of sodium gaseous atom. This is known as enthalpy, standard enthalpy change of atomization. It is the enthalpy change when 1 mole of, it's not positive, gaseous atom. Enthalpy change when 1 mole of gaseous atom, 1 mole of gaseous atom is produced from its elements sodium under standard conditions. Sodium standard state solid, so under standard conditions 1 atm pressure and 298 Kelvin temperature, and sodium is standard state solid. Now number C, here table 3.2, yes, there are some values are given. Standard enthalpy change of atomization of silver, first ionization, second ionization, bond energy, oxygen double bond, single bond, first electron affinity, second electron affinity of oxygen, first ionization energy of oxygen, and standard enthalpy change of formation of silver oxide. These values are given. So now you are asking, calculate the lattice enthalpy of silver oxide using the above data. It may be helpful to draw level cycle draw. You may draw or may not draw, no problem, but you have to show your working. You will show your calculation. You know, enthalpy of formation equal atomization, ionization, electron affinity, and lattice enthalpy. If you add, then you get the only lattice enthalpy value is not given, so if you put the other values, you will get lattice enthalpies values. Okay, now you see, first you see silver oxide will form 2Ag, then 2Ag will form 2Ag ionization, oxygen double bond break, one oxygen atom will be formed, then oxygen gains one electron, first electron affinity of oxygen, oxygen minus 2n, oxygen forms second electron affinity. So first enthalpy of formation values is given minus 31 equal 2 into 285, because silver oxide Ag2O, so here 2 silver atom will be formed. So at atomization of silver is 285, so 2 times 285, you see atomization of silver 285, so 2 silver atom, that's why times 2. Now you see, then 2 into 2 times 731, 731 is the first ionization of silver, so 2 silver ion is formed, that's why 2 into 2 times 731. Then minus 141 is the, you see, first electron affinity of oxygen, and 798 is the second electron affinity of oxygen plus lattice enthalpy. Then 496, you see 496 is the bond energy of oxygen double bond. So when it form only one oxygen atom, this divided by 2. if you put values, you will get lattice enthalpy of silver oxide minus 2968 kilojoule per mole. This is the answer. Then you see D suggests the trend in magnitude of the lattice energies to the silver compound, silver sulfide, silver oxide and silver selenium. And you see least exothermic, least value silver selenium, then most silver oxide, because oxide ion is smaller, sulfide ion is larger than oxide ion, and selenium ion is most larger, selenium. So down the groups, charge density of anion decreases. Why? Because anion become larger. All are minus negative 2, but oxygen to sulfur ion is larger, sulfur to selenium ion is larger. So their charge density of anion decreases. That's why lattice enthalpy is decreases, and silver oxide is lattice enthalpy more exothermic, and silver selenium is least exothermic, and silver sulfide is medium value. Then E, silver sulfide is sparingly soluble in water. Number 1, give an expression for the solubility product of silver sulfide. You know, silver sulfide when ionizes 2 silver ion and 1 sulfide ion is formed. If it is X, so it will be X and this will be 2X twice. So solubility of X, solubility product KSP silver ion square, because 2 silver and sulfide ion, concentration of silver ion, concentration of sulfide ion, and number of mole goes to power, here 2 power. Then calculate the equilibrium concentration of silver ion in a saturated solution of silver sulfide at 298 Kelvin temperature. Solubility product of silver sulfide is given. So now 4x cube equal this value 1.5 10 to the minus 14. 4x cube how? If you keep here 2x, so 2x square times if x, so 4x square into x, I mean 4x cube equals, so 4x cube equal 1.50 10 to the power minus 14. So if you solve it, you get x value this. So silver ion will be 2 times double, 2x is produced. So concentration of silver ion this times 2, 3.11 10 to the power minus 5 mole per dm cube. Then F, the standard enthalpy change of solution of silver nitrate in water is plus 22.6 kilojoule per mole. Suggest how the feasibility of dissolving silver nitrate in water changes with temperature. Solubility. Feasibility increases as temperature increases. Feasibility increases as temperature increases, because as T values increases, T times del S become more negative. If product of minus T T del S become more negative, so Gibbs free energy become negative. That means solubility of increases because del Z Gibbs free energy equal enthalpy change minus T del S. As temperature increases, so Gibbs free energy decreases. Gibbs free energy become negative. If Gibbs free energy become negative, solubility increases. Next, number 4. A. In aqueous solution, iron 3 ions react with iodide ion as shown. Iron 3 ion reduce and iodide ion is oxidized, redox reaction. A series of experiment is carried out using different concentration of iron 3 ion and iodide ion as shown. This is the table 4.1. Iron 3 ion concentration, iodide ion concentration, and their initial rate is given. So you are asking A. Explain what is meant by overall order of reaction. You know, the sum of the powers to which a concentration of a reactant is raised in the rate law. The sum of powers of concentration of reactant in the rate equation is known as overall order of the reaction. The sum of the powers of concentration of reactant in the rate equation are known as overall order of reaction. Next, you see to use the data in the table 4.1 to deduce the order of reaction with respect to iron 3 ion and with respect to iodide ion. Explain your reasoning. So you have to find out what's the order for iron 3 ion and what's the order of iodide ion. Now you see from experiment 1 or 2, if when concentration of iron 3 ion 3 times, keeping iodide ion constant, rate become 3 times. This times 3, you will get this value. So concentration is directly proportional to the rate, so reaction is first order. From experiment 1 or 2, when concentration of iron times 3, rate becomes 3, directly proportional. So the reaction is first order with respect to iron 3 ion. So reaction is first order with respect to iron 3 ion. Now from experiment 1 and 3, 1, 2, 3, when iron concentration is double, rate become double. As for iron 3 ion is order is 1 and concentration of iodide ion double, rate should be 2 times for first order, but rate increases 8 times. So when iron concentration double, iodide ion double, rate increases 4 times. That means when iodide ion double, rate increases 4 times for iodide ion. So the reaction is second order with respect to iodide ion. Okay. From experiment 1 or 2, if concentration of iron 3 ion double, rate become double. So the reaction is first order with respect to iron 3 ion. And from experiment 1 to 3, if concentration of iron 3 ion double and concentration of iodide ion double, so rate become 2 times, and for this 4 times, total rate increases 8 times. So the reaction is second order with respect to iodide ion. Then number 3, use your answer 2A2 to construct the rate equation for this reaction. So rate equal K means rate constant, concentration of iron 3 ion, this one order, and concentration of iodide ion second order. So 4, use your answer 2A3 and the data from experiment 1 to calculate the rate constant K for this reaction. Include the units of K for experiment 1. So K equal rate is given, concentration of iron 2 is given from experiment 1 0.4, and concentration of iodide ion 0.02 square. So you get 16.5 and mole inverse to dm cube per second. How? This is mole per dm cube per second, and this is mole per dm cube, and this is mole per dm cube square. So then remaining mole inverse to dm6 per second, you will get unit. Then 5, describe the qualitatively the effect of an increase in the temperature on the rate constant and on the rate of reaction. And you know, if you increase temperature, rate of reaction increases. So as rate reaction increases, so rate, this is the rate, as rate increases, so rate constant also increases. That means temperature increases both rate and rate constant. Next, in aqueous solution, iodide ion react with acidified hydrogen peroxide as shown. Iodide ion reacts with hydrogen peroxide acidic medium to produce iodine and water. The initial rate of reaction is found to be first order with respect to iodide ion and first order with respect to hydrogen peroxide and zero order with respect to hydrogen ion. So first order iodide ion and first order hydrogen peroxide ion. Now there are 4 steps: step 1, step 2, step 3, step 4. Now you are asking 1, suggest which of the steps 1, 2, 3 or 4 in this mechanism is the rate determining step. And you know, rate determining step involve hydrogen peroxide first order, iodine first order. So this is order 1. So step 1 will be the rate determining step 1, because this has 1 mole of H2O2, because for H2O2 order is 1, and 1 mole of iodide ion, because this given first order with respect to iodide ion and first order with respect to hydrogen peroxide. So step 1 is the rate determining step, because 1 mole of H2O2 and 1 mole of I- involved in this step. Then one, suggest which of the steps 1, 2, 3 or 4 in the mechanism is the rate determining step 1. Okay, I told. Now number 2, identify a step in figure 4.1 that involves a redox reaction. And you say step 1, because iodide ion oxidize, iodide ion oxidized from -1 to 0, and oxygen is reduced from -1 to -2. So this is a redox reaction. In step 1 you see here iodide ion -1, here iodide ion +1, iodide ion, step 1 you see iodide ion -1 to here +1, so iodide ion is oxidized and oxygen is -1 here, hydrogen peroxide oxidation number oxygen is -1, and here water oxygen is -2. So iodide ion is oxidized, oxygen is reduced, that's why it is a redox reaction. So step 1 is the redox reaction because iodide ion oxidized from -1 to 0 and oxygen is reduced from -1 to -2. Or you can write also a step 3, because step 3 you see iodide ion -1 to 0 oxidized and HiO iodine is +1, here 0, so HiO is reduced and iodide ion is oxidized. Step 3 also you can tell it is a redox reaction. Now next one, number 3, suggest the role of HiO in this mechanism, explaining your answer. Intermediate hydroiodic acid HiO role is intermediate. Why? It is produced in a step 2 and again used up in a step 3, so it is formed as intermediate. You see step 2 HiO is produced and step 3 HiO again used up. That means a role of HiO is as intermediate. Also you can write role of SiO, also you can write works as a oxidizing agent as it oxidizes iodide ion to iodine. So you can write it works, role of it is intermediate or role is oxidizing agent. Anyone you can write, you get marks. Okay, thank you dear students. Question number 5. Methylbenzene can undergo different reactions as shown in figure 5.1. This is methylbenzene, this is benzene, this is here methyl CH3 methyl. So methylbenzene reacts with hydrogen, methylbenzene reacts with bromine, reaction 2, and this is reaction 3 when methylbenzene reacts with bromine in presence of iron 3 bromide. And you know, when methylbenzene reacts with bromine in presence of ultraviolet light, free radical substitution reaction, here there are CH3, so one hydrogen will replace by bromine atom. So CH3 will be CH2Br because one hydrogen will replace by bromine atom. This is free radical substitution reaction. That's why this benzene ring, here CH3, in place of CH3 product will be CH2Br because 3 hydrogen, one hydrogen will be replaced by a bromine atom. Now This is reaction 2. Reaction 1, hydrogen, reagent hydrogen in presence of platinum catalyst. So here there are benzene, there are triple bond. So this triple bond will break down and 6 hydrogen will be added. So this will be methyl benzene will be all double bond will break down and methyl cyclohexane will be formed. This is addition reaction. Methyl benzene reacts with hydrogen in presence of platinum catalyst to form methyl cyclohexane. Reaction 3, methyl benzene reacts with bromine in presence of iron 3 bromide catalyst to form methyl bromobenzene, 2 bromomethyl benzene. Here 1, 2, 3, 4, 5, 6, 2 methyl bromobenzene, and here 1, 2, 3, 4 bromomethyl benzene. So when alkyl group is attached to benzene ring, substitution product will be second position and 4 position, because methyl group is electron donating group. If electron donating group is attached to benzene ring, substitution reaction will happen number 2 position and number 4 position. That's why when methyl benzene reacts with bromine in presence of iron 3 bromide, this is electrophilic substitution reaction. So 2 bromo methyl benzene and 4 bromo methyl benzene will be the product. Now draw the structure for the possible organic product of 3 reactions shown. I explain this. This is different product. Now number 2, complete the table 5.1. Reaction 1, type of reaction you have to write, mechanism. So reaction 1, type of reaction you write hydrogenation or reduction. Why hydrogenation? Because hydrogen is added to benzene ring, hydrogen is added. So this is, if hydrogen is added, this is known as hydrogenation, or you can write this is reduction reaction type of reaction, because if hydrogen is added, that process is known as reduction. So you can also write reduction. Then reaction 2, mechanism, free radical substitution reaction. You see, reaction 2, alkane, this methyl group, 1 hydrogen is replaced by bromine atom. So this reaction type is known as free radical substitution reaction. And when alkane reacts with halogen in presence of ultraviolet light, that reaction is free radical substitution reaction. Then number B, when methyl benzene reacts with an electrophile, a substitution reaction occurs. No addition reaction takes place under this condition. Explain why no addition reaction takes place. I mean, why substitution reaction occurs but not why addition reaction does not occur. And the substitution product is stabilized by delocalization of pi electron in the ring. And if addition reaction occur, substitution product is not stabilized. But if substitution reaction occur, then substitution product is stabilized by the delocalization of pi electron in the ring. Pi electron, this is delocalization. This delocalization, by this delocalization of pi electron, substitution product become stabilized. That's why substitution reaction occur rather than addition reaction. Next, methylbenzene reacts with thionyl bromide SOBr2 in presence of an iron 3 bromide catalyst. This product is methyl thionyl bromide is produced and hydrogen bromide. This is electrophilic substitution reaction. You see, the mechanism of this reaction is similar to that of bromination of benzene. The first step of the mechanism generates the thionyl bromide electrophile as shown here. SOBr2 positive ion, this is known as electrophile form. Now you see the reaction of methylbenzene with thionyl bromide ion is shown in figure 5.3. Complete the mechanism. You have to complete mechanism, include all relevant curly arrows and surges. Draw the structure of the organic intermediate. This is reaction mechanism is electrophilic substitution reaction. So first step you already is given, formation of an electrophile. Now second step, this is electrophile attack the benzene ring to form carbonium ion or carbocation. This is known as intermediate. So this 5 bond gives electron to electrophile, and here methylbenzene second position, 1 hydrogen is already have. So this SOBr is added with this carbon. Then as 5 bond gives electron, so this a little bit broken down. This is intermediate or carbonium ion. And third step, hydrogen ion goes away, hydrogen ion, and removal of proton, removal of hydrogen to form product. So when hydrogen go, these bond enter the ring and delocalization of pi electron again reform. Temporary disrupt here, but again here reform. So product has become stabilized. That's why substitution reaction happen here. This is free radical substitution reaction mechanism. Then you are asking next to the reaction shown in figure 2 produces small amount of byproduct P with the molecular formula this suggest a structure of the byproduct. And you see 5.2 here, this when it break down here, another methyl benzene will be added here. So this total molecule will be this. That's why this answer will be this. Here another methyl benzene is added, and this molecular formula you will get C14H14OH. OS. Next, acyl bromide RCOBr can be synthesized by the reaction of carboxylic acid and thionyl bromide. This is similar reaction to the synthesis of acyl chloride using thionyl chloride. So number 1, give an equation for the reaction between ethanoic acid and thionyl bromide. So here ethanoic acid 1 hydroxide group will replace by a bromine atom. So now CH3CO, in place of hydroxide ion you will write Br. So ethanoyl bromide, then hydrogen reacts with bromine to form hydrogen bromide and sulfur dioxide. So ethanoic acid reacts with thionyl bromide to produce ethanoyl bromide, hydrogen bromide and sulfur dioxide. Next, number 2, suggest the relative ease of hydrolysis of acyl bromide, acyl chloride and alkyl chloride. So ease of hydrolysis means reaction with aqueous sodium hydroxide. Easiest to hydrolyze first is this is acyl bromide. This hydrolysis will be most easier. Then acyl chloride RCOCl, then alkyl chloride RCl, alkyl chloride. Now explanation why. You see here CBr, in acyl bromide, here in acyl bromide, acyl chloride and alkyl chloride. So acyl bromide CBr bond is much weaker. CBr bond is weaker as bromine has a large atomic radius. Bromine radius is larger, so CBr bond is longer. If bond is longer, it is easy to break. So and reaction will be faster. In acyl chloride, carbon in CCl is more electron deficient due to electron withdrawing carbonyl group. As oxygen is taking electron, so CCl bond has become weaker. But in alkyl chloride, CCl bond is strengthened. CCl bond becomes stronger by the positive inductive effect of alkyl group. As alkyl group is electron donating group, so RCl bond becomes strong, so hydrolysis will not be easier. Hydrolysis reaction will be hardest. So first, easiest this. Why? CBr bond is longer, so it is easier to break. Why CBr bond is longer? Because bromine atom is larger, radius of bromine atom is larger, and in CCl, RCOCl, CO group is attracting electron, so here CCl bond become weaker, but in RCl alkyl group is electron donating group, so here electron density is increases and hydrolysis become harder. Next, number 6, perindopril is a drug used to treat heart disease. So this is an organic compound. And number 1, state the number of chiral carbon atoms present in one molecule of this compound. Five. This 1, 2, 3, 4, 5. So chiral carbon atom 5. Then number 2, suggest one benefit and one disadvantage of producing a drug, say perindopril, as a single pure optical isomer. And you know, benefit, advantage, if single optical isomer is produced, this advantage or benefit will be less side effect or higher biological activity, or you can write a smaller dose is needed, a smaller dose is required. And disadvantages, separation is needed, or you can write lower yield is less. Now B1, name all the functional groups in perindopril. Functional group here carboxylic, star, amide, amine. You see, these are star, these are amine, CONS is amide, and this is carboxyl group. So 4 functional group is star, amine, amide and carboxylic acid. Next, number 2, a sample of perindopril is hydrolyzed with hot aqueous acid. Draw the structure of 3 organic products of the complete acid hydrolysis of perindopril. And you see acid hydrolysis reaction with acid and water, and you see as here functional group star, so this part will be methanol, CH3CH2OH, ethanol, sorry, here 2 carbon, 1, 2 carbon, 2 carbon will be ethanol. Then here also hydrolysis, this part will be NH and COOH, this will be carboxylic acid. So this product, 1 product, 2 product, remaining 3 product. Now you see the answer. Ethanol, CH3CH2OH, ethanol, 1 product, and other product you see this. How? N, here hydrolysis H will be added, and remaining COOH. And other product here COOH will be added. So you see again here one product CH3CH2OH, here COOH will be added, carboxylic acid, and also here this will be OH, another product, this second product, and here NH will be added. So three organic compound you will get. Now number 7, explain why phenol is brominated much more easily than benzene. Then benzene is brominated, and you know phenol OH group is added. This is phenol. That means phenol is brominated. Phenol reacts with bromine more easily. Why? Than benzene. You see, lone pair, oxygen has two lone pair. Lone pair from oxygen atom overlap into the ring. This lone pair electron overlap with benzene ring. Lone pair from oxygen atom overlap into the ring. This makes the ring more electron rich. As lone pair is coming here, so here electron density increases, benzene ring become more electron rich. As more electron rich, so electrophiles are polarized more easily, or electrophile is susceptible to attack benzene ring. That's why phenol is brominated more easily compared to benzene. Number B, iodine monochloride IBr reacts with benzene in the presence of aluminum bromide catalyst. Predict whether the organic product will bromobenzene or iodobenzene. So you know IBr, so bromine is more electronegative, so this will be negative, electrophile will be I plus, so product will be iodobenzene, because bromine is more electronegative than iodine, so here electrophile will be I plus, that's why product will be iodobenzene. Next, you see this figure 7.1 shows some reaction of phenol. This is the phenol, excess bromine R, sodium to produce Q, and reaction 1 nitrophenol, 4 nitrophenol, reaction 2 azo compound, 4 hydroxy phenyl azo benzene is formed. You are asking number A, give an equation for the reaction of phenol with with sodium. And you know, when phenol reacts with sodium, this reaction, this hydrogen will be replaced by sodium. Sodium phenoxide plus hydrogen will be produced. You know, phenol reacts with sodium to produce sodium phenoxide plus hydrogen. So here C6H5OH, sodium, hydrogen will replace by sodium. Oxide is minus, sodium is plus. but if you don't write plus and minus, this is no problem. Plus hydrogen, half hydrogen is produced. Next, you see number 2, draw the structure of the organic product R form when phenol reacts with excess bromine. You know, phenol OH group is electron donating group. So when phenol reacts with bromine to form 2,4,6 tribromophenol. This is phenol. So when it OH group is electron donating group, if electron donating group is attached to benzene ring, substitution atom will be added to 2, 4 and 6 number carbon. Here this is 1, this is 2, this is 3, 4, 5, 6 carbon. So this name will be 2 carbon 4 6 2 4 6 tribromophenol. Phenol reacts with bromine, excess bromine, to produce 2 4 6 tribromophenol. Then state the reagent and condition for reaction 1 and reaction 2. Reaction 1, dilute nitric acid, because you see phenol 2 NO2 4 nitrophenol. So nitro group is produced from nitric acid. So reagent is aqueous nitric acid or dilute nitric acid. Then reaction 2, you see benzene diazonium chloride condition in alkaline or in presence of alkali, in presence of sodium hydroxide. Now you see reaction 2, phenol produces 4-hydroxyphenyl azobenzene. This part benzene diazonium ion. So phenol reacts with benzene diazonium chloride to produce 4-hydroxyphenyl azobenzene. That's why reagent will be benzene diazonium chloride, benzene diazonium salt, and this reaction will occur in alkaline condition or in presence of sodium hydroxide. Thank you, dear students. Please subscribe, like and share my channel. Thank you. Question number 8. A. Describe the difference in reactivity between chloroethane and chlorobenzene with hydroxide ion, aqueous hydroxide ion. Explain your answer. Chloroethane CH3 CH2 Cl, chloroethane, and chlorobenzene, this is chlorobenzene, So chlorobenzene is less reactive than chloroethane. Chlorobenzene is less reactive than chloroethane. Why? Because lone pair on chlorine has lone pair, 3 lone pair. Lone pair on chlorine will overlap into the ring. This lone pair electron will go to the benzene ring and mix with delocalized electron. So this carbon-carbon chlorine-carbon bond likes to double bond. So lone pair on chlorine will overlap into the ring. So CCl bond is strengthened. CCl bond become stronger due to partial double CCl bond. As due to delocalization, this carbon chlorine bond become double bond. So double bond is stronger, that's why chlorobenzene is less reactive. So chlorobenzene is less reactive than chloroethane because lone pair on chlorine will overlap into the ring. So CCl bond carbon chlorobenzene, in chlorobenzene this CCl bond, this bond CCl bond is strengthened. CCl bond has become strong due to partial double carbon chlorine bond. That's why chlorobenzene is less reactive. Now next one, B, compound T. This is compound T. C5H9 O2Cl is useful synthetic intermediate. Figure 8.1 shows some reaction of T. Here T reacts with excess sodium hydroxide and heat, and reaction 1, it Cl converted to CN, cyanide compound, and this compound reacts with excess hydrochloric acid and heat, and step 2 CN group converted to CH2 NH2. So first you see this, number 2, draw the structure of W, X, Y and Z in figure 8.1. You see the answer. So when compound T reacts with excess sodium hydroxide, and you know, first here has star group and has chlorine group. So this star hydrolysis of star by alkali. So alcohol and sodium salt of carboxylic acid will form. So here CH3, CH2, this oxygen takes hydrogen, so CH3, CH2, OH. Ethanol will be X is ethanol. Now W, sodium salt of carboxylic acid, so carbon oxygen double bond, and here ONA, sodium salt of carboxylic acid, and as excess sodium hydroxide, so this chlorine atom will also substitute by hydroxide ion. So hydroxy sodium salt of carboxylic acid plus ethanol is produced. Then step 1, you see chlorine goes to cyanide, nitrile compound. Then when nitrile compound and also star COO when it reacts with excess aqueous hydrochloric acid, and hydrolysis of ester is from alcohol is given here, breakdown CH3 CH2 OH, alcohol is from ethanol, then carboxylic acids, so CO, that's OH will be added to form carboxylic acid, so carbon oxygen double bond, also OH, carboxylic acid, then CH2 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 same, and CN converted to carboxyl group also, cyanide compound or nitrile compound acid hydrolysis converted to COOH, carboxylic acid. So here two group react, one is ester reaction, other is nitrile compound hydrolyzed to produce carboxylic acid. Then and this compound step 2 produces here 6 carbon, 1 2 3 4 5 6 carbon same, hydrogen 4 hydrogen more, 4 hydrogen atom more here, so here 3 5 7 9 hydrogen, but here 13 hydrogen, so 4 hydrogen will be increased. Why? Because cyanide group CN group reduce to CH2 NH2 group. So here 2 hydrogen, here 2 hydrogen, 4 hydrogen has increased in compound Z. That's why step 2 hydrolysis, reduction of nitrile compound converted to CH2 NH2, remaining CH3 CH2O CO CH2 CH2 remains same. Only cyanide ion nitrile group converted to CH2 NH2. Then next give the systematic name for T, give the systematic name for T, ethyl 3-chloropropanoate, T you see name ethyl, here CH3 CH2 ethyl 1 2 3, number 3 carbon contains chlorine, ethyl 3-chloro 1 2 3 carbon alkanoate is propanoate. So the systematic name of T will be ethyl 3-chloropropanoate. Ethyl 3-chloropropanoate. This is the one. Number 2 I already discussed. Now number 3, state the reagents and conditions for step 1 and step 2. And you see step 1 reagent potassium cyanide condition in ethanol. So step 1 you see what happened. Step 1 this remain same, only haloalkane converted to nitrile compound, cyanide compound. So reagent will be potassium cyanide and potassium cyanide dissolve in ethanol. Condition will be dissolve in ethanol. Next, you see number 3, state the reagents and condition for step 1, potassium cyanide in ethanol, or you can write heat. Step 2, hydrogen plus nickel, or you can write hydrogen platinum, or you can write lithium aluminum hydride. And lithium aluminum hydride reduction reaction. Step 2, you see CN group converted to CH2 and H2. So hydrogen is added. This reaction is reduction reaction, reducing agent lithium aluminum hydride, or you can write hydrogen in presence of nickel catalyst, hydrogen plus platinum condition, lithium aluminum hydride condition in dry ether. When you use lithium aluminum hydride, condition will be dry ether. Now next, the proton means hydrogen NMR, nuclear magnetic resonance of a spectrum of T in CdCl2 deuterated chloroform. This is deuterated chloroform is solvent, is shown this diagram. Now here different and environmental proton and their which proton are responsible and their chemical shift ppm, chemical shift unit ppm values are given. So now you are asking question, suggest why deuterated chloroform CdCl2 is used as solvent instead of chloroform for the proton NMR spectrum. And you know CdCl3 has no proton, there is no proton, so CdCl3 does not give a peak. As proton NMR there is no proton here, so it will not give any peak, but chloroform has hydrogen, so it will produce A1 peak, it will give peak. Then and complete table 8.2 for the proton NMR spectrum of T, and you see T compound is this, this is the T, this is T, this is an ester and also chlorine atom. So this is T, compound T. Now you are asking chemical shift is given 1.2, environment of proton, this means which proton gives 1.2 chemical shift, and splitting pattern means it will be doublet or triplet or quartet. Then number of hydrogen atoms responsible for this peak, which proton, the number of protons that gives this peak. You see 1.2, this is 1.2 CH3. CH3 proton is responsible for peak at chemical shift 1.2, and this will be triplet. Why? Because here CH3 there are CH2, 2 proton, so splitting pattern will be n plus 1 rule. N is the neighboring proton, so CH3 neighboring proton is 2, here 2 proton, 2 hydrogen, so 2 hydrogen plus 1, 3 hydrogen, that will be triplet. And number of hydrogen atoms responsible for this peak here as CH3, that means number of hydrogen is 3. Then 2.8 is responsible for CH2CO, this peak. Here this is 2.8, this is CH2 and carbon oxygen double bond, this group. And splitting pattern triplet, why? Because there are here 2 proton here, 2 hydrogen atom, so n plus 1 rule, it will be 2 plus 1, 3 peak, triplet. 3 peak is known as triplet. Number of proton responsible for this peak here 2 proton, 2, as 1 2 bond already present, so here CH2, this CH2 means 2 hydrogen. 3.7 is this 3.7 chemical shift is responsible for this CH2 peak. So this will also be triplet, why? Because CH2 neighboring proton is also CH2, so 2 proton, 2 plus 1, 3 peak, triplet. And number of hydrogen atom responsible for this peak 2 hydrogen, because CH2 means 2 hydrogen. Then 3.9 chemical shift is higher, as electronegative is atom is joined to hydrogen, chemical shift will be more. So this 3.9 is responsible for this CH2O, this 3.9. So this neighboring proton is CH3, so splitting pattern will be quartet. CH3 means 3 proton, n plus 1 rule, so it will be quartet. And number of hydrogen atom responsible for this peak, so this will be 2, because CH2. This is for environment of the photon and splitting pattern and number of hydrogen atom responsible for this peak. Next you are asking, explain the splitting pattern of the peak at 3.99. There are 3 hydrogen on neighboring carbon, as 3.9 quartet means 4 peak, so neighboring proton is 3, that's why 3 plus 1, n plus 1 rule, so there are 3 hydrogen on neighboring carbon or on adjacent carbon, you can write. Next, number 9. Define the standard cell potential E cell. The potential difference between the two half cells under standard conditions. The potential difference between the two half cells under standard conditions. The potential difference between the two half cells under standard conditions. This is define the term standard cell potential. The potential difference between the two half cells under standard conditions is known as standard cell potential. Then number B, an electrochemical cell is set up to measure standard electrode potential of a cell consisting of iron 3, iron 2 half cell and chlorine Cl minus half cell. Draw a level diagram of this electrochemical cell. Include all necessary substances. It is not necessary to state condition used. So here right hand is positive electrode, iron 3 ion aqueous solution, iron 2 ion aqueous solution, platinum electrode. Then left hand electrode, platinum electrode and chloride ion 1 mole per dm cube solution. Chlorine gas is pass this half cell, and voltmeter, 2 half cell is connected salt bridge. This is the diagram. Then number C, the cell reaction for the electrochemical cell in B is shown this: chlorine reduce and iron 2 oxidize. Standard electrode potential of this cell is given. So calculate standard Gibbs free energy in kilojoule per mole for this cell reaction. And you know formula: standard Gibbs free energy change equal minus NF E cell naught. So N is the number of electron. Here when chlorine goes to chloride, 2 electron, and iron goes to minus electron, then same number of electrons, so total electron will be 2. F is the Faraday constant, 96,500 coulomb, and electrode potential of this cell is given plus 0.59. So if you calculate, you get this joule per mole, then divide by 1000, you will get minus 114 kilojoule per mole. This is the standard Gibbs free energy, minus 114 kilojoule per mole. Now number D, another experiment is set up using the same electrochemical cell. In this experiment, iron 2 ion concentration is 0.15 mole per dm cube. This is not in standard condition. All other measure concentration remain at their standard values. The Nernst equation is given. So number 1, use this equation to calculate the electrode potential E for the iron half cell in this experiment, and to calculate electrode potential E of iron 3 half cell, non-standard condition E cell. So standard electrode potential of half cell is given plus 0.77, and now E cell E naught value is given, and 0.059 and this 1 log this 1, this 0.15. So if you calculate, you get 0.82 volt for this equation. You can then use use your answer to D1 to calculate E cell for this electrochemical cell. Use U1, then E cell you will calculate. So you can E cell 0.59 plus 0.77 and minus this, you get this value plus 0.54 volt, or you can write it, you can solve it. Reduction minus oxidation equal given plus 0.59. This is given previous question. Here 0.59. Then so reduction chlorine half cell equal this plus this, you get plus 1.36 volt. Then now E cell will be chlorine half cell plus reduction half cell minus oxidation half cell iron, so you get plus 0.54 volt. This is the answer. Thank you, dear students.